Alright, our last example of curve sketching, and it is finally one that has vertical asymptotes. So that domain, when we look at that denominator, since it is x squared minus 4, actually we cannot plug in the values of 2 or negative 2. So x cannot equal plus or minus 2, which means we have vertical asymptotes at x equals plus or minus 2. And the next thing we would look at, we are still going to have an in behavior. We still have a horizontal asymptote. So in behavior, horizontal asymptote at, look at the degree of our numerator, it is 2. The degree of our denominator is 2. And they are equal, so what does that mean? That means we have a horizontal asymptote at the ratio of the leading coefficients, which is y equals 1. Okay, y-intercept, plug in x equals 0, and you get 0. X-intercept, well, that numerator is only going to be 0 when x is 0, so x-intercept is also 0, 0. Okay, now we are doing the first derivative test, increasing, decreasing, any maximums and where they are, any minimums and where they are. So this is a quotient rule. The derivative of both the numerator and denominator is 2x. So let's plug into our derivative, f prime of x equals low d high, that will be 2x times x squared minus 4, minus high d low, that's going to be 2x times x squared, all over low squared quantity x squared minus 4 squared. And if I multiply this out, keep it over x squared minus 4 quantity squared, I get a 2x to the third minus 8x minus 2x to the third. So those 2x to the thirds cancel out. And that means my first derivative, f prime of x, is negative 8x divided by x squared minus 4 quantity squared. Okay, to do our first derivative test, we have to find our fence posts, which occur at our critical numbers. So this time you have two critical numbers where your derivative does not exist. Where are those? They are at plus and minus 2, that's where your denominator is 0. And you have one critical number where your numerator is 0, where your function is 0, and that's at 0. So fence post at 0, at negative 2, and at positive 2. Okay, let's plug in, let's try negative 3. And again, the denominator, x squared minus 4, since I'm squaring that, that's always positive. So really I'm looking at the numerator to tell me if my derivative is negative or positive. And if I plug in negative 3, it's going to be positive, which means that my function is increasing. Okay, let's try negative 1. And if I plug that in, I still get a positive, so my function is still increasing. And let's try positive 1, and if I plug that in, that's a negative, so my function is decreasing. And if I plug in x equals 3, that's a negative, so it's still decreasing. So we go increase, increase, decrease, decrease, so looks like we have a max at 0 and then no mins. So interval of increase, I have to write this as 2 intervals because the fence post negative 2 was a vertical asymptote. Our function is not defined there. So we are increasing from negative infinity to negative 2, union negative 2 to 0. We are decreasing from 0 to 2. Same thing with the 2, it's a asymptote, so I can't include it. And 2 to infinity. We have a maximum at 0, and to find that y value, we plug it into the original, which is also 0. And no minimums. We did not go from decreasing to increasing. Okay, now it's time for finding the concavity, concave up, concave down, and any inflection points we might have, and that's a second derivative test. So let's rewrite our first derivative here. Put it over here. So our first derivative was negative 8x over x squared minus 4 squared. So derivative of the numerator is negative 8. I'm doing a quotient rule again. Derivative of the denominator, if you do chain rule, you get 4x times x squared minus 4. So let's plug that into our second derivative, f double prime of x. Low d high, that's going to be negative 8 times x squared minus 4 quantity squared, minus high, since that's a negative, I'm going to make that plus 8x, times d low, 4x, times x squared minus 4, all over low squared, and I'm squaring a square, so that's a power of 4. And again, we have an x squared minus 4 in each and every term, so cancel one of them out. That one goes away. That's a power of 3. That would be a power of 1. So f double prime of x equals, multiply the negative 8 into the x squared minus 4, I get negative 8x squared. That'll be plus 32, 8 times 4. That's a 2. And then, let's see, multiply the 8x and the 4x, so we get a 32x squared. Okay, and then all over x squared minus 4 to the third. And we can do some simplifying here, combining our x squared terms. So let's see, we've got a negative 8 and a 32. That's going to give us 24x squared plus the 32 all over x squared minus 4 quantity cubed. And let's see, what do those have in common? They have an 8 in common, so let's factor that out. I get 3x squared plus 4. So now to do my fence post for my second derivative test. Again, where's my second derivative undefined? I do have places in this problem because I have x squared minus 4 in my denominator. That's going to equal 0 at negative 2 and at positive 2. And is there anywhere my second derivative is 0? Well, no, because that 3x squared plus 4, if I set that equal to 0 and solve, I get an imaginary number. So negative 2 and 2 are my only fence posts in this. So let's try negative 3. Plug in negative 3. Now this time I have x squared minus 4 in my denominator, and I'm cubing that. I'm not raising it to an even power, so that possibly could be a negative or positive number. So I really do have to pay attention as to what the denominator is. But the numerator, 8 times 3x squared plus 4, that's always going to be positive no matter what. So really this time I'm looking at the denominator. So if I plug in negative 3, I'm going to get 9 minus 4, which is 5. 5 cubed is a positive number, that's concave up. If I try 0 and the next one, I get negative 4 cubed, that'll be a negative number, concave down. And then if I try positive 3 in the next interval, I'm going to get positive, concave up. So we have concave up intervals from negative infinity to negative 2, and from 2 to infinity. And we are concave down between negative 2 and positive 2. And inflection points, well, our concavity changes at 2 and minus 2, but remember that those were vertical asymptotes. They're not actually points on our graph, so there actually are no inflection points in this graph. Okay, let's graph our points. We had y-intercept and actually x-intercept was at 0, 0. Those were the only intercepts we had. We had a max at 0, 0 and no mins. And we don't have any inflection points. So let's sketch in our vertical asymptotes, one at negative 2, one at positive 2, and we had a horizontal asymptote at y equals 1. So in the long run, it will level out at y equals 1. Okay. So I'm going to have 3 pieces of this graph between the 3 different divisions I've made from my 2 vertical asymptotes. The first one, to the left of negative 2, my function is increasing. I know it's increasing negative infinity to negative 2, and it is concave up. So it has to level out at the horizontal asymptote. It's got to look something like this, kind of like a boomerang. Okay, and then my function is going to be increasing still from -2 to 0, and it's actually going to be concave down in this part now. So concave down looks like this, increasing but concave down. And then 0, 0 was a max, so from 0 to +2 it says that we are decreasing but still concave down. So something like this, kind of like an upside down parabola. Concave down on that whole time, changes from increasing to decreasing. And then our third piece, we know that we are decreasing from 2 to infinity, but we are also concave up, and we know that we have to level out by our horizontal asymptote in the long run, so it's going to look also kind of the reverse of what we had on the left hand side there. And that's our graph.